Hello everybody. I think it's time to get going. Welcome back for one last week. So I sent an email earlier this morning concerning, my plans for the last week of class. What I want to do is today, just sort of typical, I'm going to do more problems from the sections for this week, which is about fundamental theorem calculus and the area of curved shapes. And then tomorrow is going to be our review for the final exam. So I will make up a review sheet and go over problems from the whole semester. And then Friday is going to be our usual Friday, which is, you guys finishing up the homework, and then we do the quiz at the end of class on Friday. Otherwise, I would like to encourage you to do the class evaluation survey. I don't think I'm going to set aside time during class to do it, but I hope that you will take 5 minutes or so, however long it takes to do those. I put links to the survey at the class website near the homework assignments, so you should be able to find it. Check it out. I do appreciate any comments that you have about how the course went. Obviously it's a very strange semester, but I hope that you learned something. I think you did. Are there any questions about the logistics of our last week together, or anything else before we get down to it? All right. Well, let me know. I am happy to send a report about your grades if you like. If you're wondering, exactly what you're looking at for your grades so far, let me know. I would be happy to send you something about that. All right. Okay, I guess we'll just get down to it then. I want to do some examples concerning the fundamental theorem of calculus and also finding the area of curved regions. Fundamental theorem of calculus. The fundamental theorem of calculus really is the making clear the connection between the definite integral, which is the area under the curve, and the indefinite integral, which is the antiderivative. We call them both integrals because they actually are very closely related, even though they seem to be two completely different concepts. But it turns out there is a deep and abiding relationship between them, and here it is. This is the fundamental theorem of calculus. It says the definite integral from a to b of f of x dx, that is the area under the curve, from x equal a up to x equal b. This equals big F of b minus big F of a, where the big F is the antiderivative of the little f. The big F is the antiderivative of the little f. All right, this is called the fundamental theorem of calculus. It's super important. It's a shame that we're only getting to it, in the last week here, but if you go on to take Calc 2, you'll be doing this, all the time, every day. Maybe not every day, but all the time. All right? Or if you use calculus in physics or something like that, you use the fundamental theorem of calculus all the time. Okay, this is the way to find the true value of a definite integral, the actual answer, right? We've been talking the past week about how to estimate the definite integral by various different strategies. What with the rectangles and the midpoints and all that, or the trapezoid-Simpson's rule. Those are all estimations of the actual area. If you want to know what the true area is exactly, you do it this way, the fundamental theorem of calculus. Perhaps you wonder, if we have a way to do the actual answer, then what was the point of talking about estimating the answer? All that, we spent a whole week talking about estimations. Why do we do that if just the very next week we figure out how to compute the true answer? Well, that's because in order to do the fundamental theorem calculus, to find the true answer, it requires that you have a formula for the function and you can find the antiderivative. This is usually the case in a math class. Usually they give you a formula and then your job is to find the integrals. But if you're using the integral in the real world, many situations you will not have a formula for whatever you're studying. as I've said in the past. You know, in physics, things obey formulas, rules, laws, but in other fields, they really don't. And all you get is data or graphs or whatever. And in that case, you cannot use the fundamental theorem of calculus because you can't find the antiderivatives. You have to just do the Simpson's rule or something like that. All right, anyway, let's just get to the example. So I want to do several of these. All right, first one, let's try the integral from -1 to 2, 3x to the 4 minus 7x squared plus 4 dx. All right. When you are doing one of these, the first thing you do is write the antiderivative. So, what is the antiderivative? Can somebody shout it out for me? Well, I got this extra line there. Somebody tell me, what's the antiderivative of all of that? I hope you remember antiderivatives.
Is it 3 times 1/5 x to the 5th minus 7 1/3 x to the 3rd plus 4x?
I like that, yeah. Excellent. This is a typical sort of easy antiderivative, right? You use this, since it's a polynomial, you should be every time increasing the power by 1 and then dividing by the new power out front. All right, this is the antiderivative. And then when I'm doing the fundamental theorem of calculus, the way that we write this is you write the antiderivative and then you put this bar with the two interval endpoints, the -1 and the 2. All right, so the bar indicates that I have already done the antiderivative, but in the next step, I'm going to plug in the 2 and the -1. That's what this over here means. You plug in the top number, and then you subtract, and you plug in the bottom number. So this, this bar here is an indication that in the next step, I intend to plug in the 2 to this whole formula, and then subtract, and then plug in the -1 to that whole same formula. All right, when we write, the bar always goes on the end, like on the right side. The integral sign always goes on the left side. Just the way we do it. Okay, what do we do? I'm going to plug in 2 for x everywhere, so it becomes 3 times 1/5 times 2 to the 5th minus 7 times 1/3 times 2 to the 3rd plus 4 times 2. All right. That was the f of b part. I plugged in 2 everywhere. And then I go minus, I'm going to go through the whole thing again, plugging in -1 everywhere. You better have them parentheses there. What? -1 to the 5 minus 7 times 1/3 minus 1 to the 3 plus 4 times -1. There it is. And this is the answer. That's the actual area under the curve. If you want, you can plug all of that into a calculator if you want to see what the number is. But I don't care about that so much. This is the area under the curve. Any questions about that one? This, I would say, is a fairly straightforward one. Somebody got a question? No. Okay, let's do some more. That one was fairly straightforward, I said, just because the antiderivative is pretty easy to do. In that case, it's a polynomial. How about this? Integral from 3 to 10, e to the 2x plus 1 over x dx. All right, similar procedure, only the function is a little bit stranger. You have to remember, how do you do integral of e to the 2x? And then also, how do you do integral of 1 over x? So for the e part, you will, I hope, remember, this was one of the rules that we had discussed when we talked about exponential functions and the derivatives and antiderivatives of exponential functions. Ooh, I just adjusted my chair and now my neck feels much better. Integral e to the kx. I hope you remember. It's fine if you don't remember. I hope you have this written down somewhere so that you could look it up if you wanted to. Integral of e to the kx is 1 over k e to the kx plus c. Now, when we do the definite integral problems, the fundamental theorem, you never have to write the plus c because they will always cancel out if you do it properly. I discussed that in the video. What about 1 over x? Anybody remember what is the integral of 1 over x? Anybody remember how you handle this one?
Is it ln x?
It is,
Like,
yeah, the natural log.
Absolute value of x?
Absolute value of x. Yeah, great. So these are two sort of facts from your past like 2 weeks ago that I hope you remember how to do these antiderivatives. All right. Anyway, since I know those two antiderivatives, it should be pretty easy to do the problem at hand. I begin by doing the antiderivative. So e to the 2x, I'm going to use the formula on the right there, but where the k is 2, it becomes 1 over 2 e to the 2x. All right. I used this formula here with k equal 2. And then I go plus, and what happens to the 1 over x? 1 over x, the antiderivative is natural log absolute value x. All right. I'm not going to put the plus c's like I said before. When you're doing the fundamental theorem of calculus, you never need the plus c's because they're going to cancel out anyway. I am going to put the bar 10 and 3, right? These are the values that I need to plug in. And let's plug them in. I go through the whole thing, put 10 in for x everywhere. So it's 1/2 e to the 2 times 10 plus natural log absolute value 10. And then I go minus. I'll go through the whole thing, plug in 3 everywhere. 1/2 e to the 2 times 3 plus natural log absolute value 3. And this is my answer. Make sure you have the parentheses there. These parentheses are important because these parentheses indicate that this minus sign here, really it affects both of these terms. The minus sign needs to distribute across there if you were really evaluating this thing in that way. If you left out the parentheses, then the minus sign would only go on the first term there, which is not what you mean. That's different. So you need the parentheses to be there. All right. Any questions about that one? This was a slightly more difficult one because the things are a little bit weirder to do in the integral. Okay, let's try another one. This one's going to be quite a bit more difficult. Let's try integral from 1 to 3 x over x squared plus 1. All right. This one is quite a bit more difficult because it's a much weirder function on the inside of the integral sign there, and you cannot just easily find the antiderivative. In this one, actually, you need to do the substitution, the u substitution. You have to do the u substitution because that thing on the inside of the integral is too complicated. It's a fraction. You can't just do the integral on top and also the integral on the bottom. We all know that. Do you remember how to do the u substitution? I know it's been a couple weeks since we did this. I hope you remember. Anybody remember the basics? What should I choose for the u here?
The denominator.
Yeah, let's choose the denominator. Usually you use something which is like the inside of parentheses, the inside of a square root sign, the inside of an exponent. But if all that fails, sometimes you just have to pick parts. If you see a fraction without any parentheses anywhere, it's generally a good idea to choose the denominator. Let's try it. U equals x squared plus 1. Then the du is 2x dx. Right? And if you recall, when you're doing u substitution, you often are going to have a constant there, which you divide to the other side. And I happen to know how this one's going to work out. It will be helpful for us to divide the constant and make 1/2 to u equals x times dx. Anyway, let's do the substitution. So this right here becomes integral. I will begin the substitution by just plugging u into wherever it goes. So u is the denominator, so I put u in the denominator. All right, what can we do with this? Now, I like to sort of separate out the u stuff from the stuff which is still in terms of x's. So I'm going to write this like 1 over u times x times dx. All right, I'm trying to move apart the x's and the u's. The way to split up a fraction like that is to just kind of split out the numerator from its denominator. Of course, the denominator has to stay in a denominator, but it looks like that. And now what can I do with x times dx? this x times dx is the same as what we see up there. It is 1/2 du. So this is integral 1 over u times 1/2 du. And now I have replaced all the x's with u's, right? There are no more x's remaining. And so now it's time to do the antiderivative. First I can, this 1/2 on the inside there is a little inconvenient. Remember, a constant multiple inside an integral can be pulled all the way out. So it's the same as 1/2 integral 1 over u to u. All right? And finally, we are ready to do the antiderivative. What do you say? What's the integral, the antiderivative of 1 over u? I get the 1/2. We'll just stay like it is. Integral of 1 over u is, what do you think? Antiderivative of 1 over u. I'm going to have a sip.
Is it ln u?
It is ln of absolute value of u. Excellent. Yeah, remember we just did one like that a moment ago, right? In that case, it was 1 over x, you get ln absolute value x. 1 over u, you get ln absolute value u. All right, excellent. The very last step of the u substitution, as always, is to put the x's back in. So my u substitution completes, or my, this whole thing is finding the antiderivative. And now I have actually found the antiderivative of the original function. 1/2 natural log x squared plus 1. All right. Now, in an ordinary indefinite integral, you would put the plus c and be done at this point. But this is a definite integral from 1 to 3. So instead of putting the plus c, I put the bar and the 1 and the 3. And now I got to plug in the 3, subtract, plug in the 1. So you just go through this whole thing, put a 3 in for x. So it's 1/2 ln absolute value 3 squared plus 1 minus, and then I go through the whole thing again, putting a 1 for x. 1/2 ln absolute value 1 squared plus 1. And that is my answer. As always, you can plug this into your calculator if you want. It's a number. All right. Any thoughts about that one? Questions? Okay, those are all the examples that I wanted to do from that section, which was the fundamental theorem of calculus section. The next section, which is the final section, concerns finding areas using the integral. Areas. All right. You can use the integral to find the area of a curvy shape. That's what the definite integral represents. It's the area under the curve. Let's just try some. So I got 2 examples. The first is a little easier. The second is a little harder. That's how it works. Find the area between the x-axis and this thing here. Y equals x squared minus 3x minus 4. All right? So this is your job. This will involve an integral. The integral actually, once you get to that point, is not a hard integral to do. The hard part about this problem is figuring out how to set up the appropriate integral. So the curve here, y equals that stuff, I happen to know a little bit about graphs of such things. This looks like a parabola, right? And the x squared having a positive coefficient means it's a parabola which sort of faces up, uppity parabola. So this, I don't really know what exactly it looks like, but something like that. Don't take my word for it. Like the actual positioning of this is probably not accurate. I just randomly drew a parabola going up. But anyway, the area that we're trying to figure out is this area here, right? And what makes it difficult is we don't know what these 2 points are. Those 2 points will fill in. What we want to do to find the area is this, right? The integral x squared minus 3x minus 4 dx with some numbers here and here, right? And those numbers come from these 2 values. This one should be the lower value, and this one should be the upper value, right? So in order to set up the integral, you need those two numbers, and those two numbers are going to be those 2 points with the red arrows pointing at them. Anybody want to suggest how could we find those 2 points?
Find the x-intercepts.
Yeah, these points are the x-intercepts, and it's not too hard to find x-intercepts. How do you do that?
Solve out the equation.
You solve them using the equation. Yeah. How in particular, what do you do with the equation?
Oh, don't you have to set it equal to 0 or something?
Right, you set y equal to 0 and then solve for x. Yeah, thank you. So I'm going to set y equals 0, solve for x. And hopefully I'll get 2 answers, and those are those 2 numbers. Let's see what happens. So I have this, y equal x squared minus 4. I set that equal to 0. So x squared minus 3x minus 4 equals 0. How do we solve this for x? You better factor it. Any factorers out there? What do you get when you do the factors?
X minus 4, x plus 1.
I like it. Yeah, x minus 4 and x plus 1. And so that means x minus 4 equals 0, x plus 1 equals 0, x equals 4, x equal minus 1. So actually, it looks like my picture was actually fairly accurate. This is minus 1, and this is 4, which is pretty, you know, I could believe that, right? It's pretty good. I just made that up. I actually hadn't worked this one out ahead of time. All right. Okay, we're not done yet, but all of this is like the preamble to set up the integral. Once you have the integral set up, it's easy to do the integral. This was all the setup. So my actual answer then, the area is the integral from, I use those 2 numbers that I just found, from -1 up to 4 of this function, x squared minus 3x minus 4 dx. And now let's actually do the integral. This is an easy integral to do. It's like the very first one that I did at the top there. You go through the polynomial and do the antiderivative. Can somebody shout out for me the antiderivative?
Wouldn't it be 1/3 x to the 3rd minus 3x, sorry, 3 to the 1/2 x squared minus 4x?
Yeah, 3 times 1/2 x squared minus 4x. Excellent. Yeah, that's the antiderivative. And then I'm going to put my bar here, plugging in 4 and -1. And we go through and do it. So negative, no, not negative, just 1/3, 4 cubed, minus 3 times 1/2, 4 squared, minus 4 times 4, minus, parentheses, 1/3, -1 cubed, minus 3 times 1/2, -1 squared, minus 4 times -1. Like so. And this is the answer. That's the area of the shaded region. You don't really need to see the picture at all. The only thing that really matters is where those 2 points are. But if you think about it, I think you'll agree with me. You don't even need the picture to find the points, right? I found the points without looking at the picture. So, you know, really knowing what the picture looks like is not necessary to do this whole problem. You have to know what to do, but you don't actually have to see the picture. Questions about that one? I got one more. All right, let's do one more. Let's try. This one is slightly trickier. Find the area between the x-axis and y equals x plus 4, let's say, on the interval minus 10 to 10. All right, this one involves another kind of complication. So we have minus 10 to 10, and this function is x plus 4, which I happen to know has a y-intercept of 4 and a slope of 1, so it looks something like this. All right, and what we are looking for is the area between the x-axis and this straight line. That would be this area and also this area. All right, that's what the question is looking for. Find the area between the x-axis and this line. You may be tempted, but it's not. I'm just going to say it's not integral minus 10 to 10 of x plus 4 dx. That would be too easy. All right, why is it not that? It's because of the way that the integral measures area. This is something I discussed in detail in the video. The integral, when you do the integral, this part of the area will be measured as if it was positive, and this part of the area will be measured as negative. And so if you do this entire integral like this, what you're going to do is sort of add up all of these areas, but there will be some sort of cancellation. This little piece will cancel off part of the big piece. And you'll get the wrong answer. Like, really, what we do not want those areas to cancel each other out. If I really want to know what's the total shaded area on the picture there, you cannot like cancel some of those two areas with each other. I want to know the actual total area that's shaded in. So you cannot do that integral. What you have to do is we need to split it up. Split it up when it crosses the x-axis. In other words, we do them separately, those two pieces. There's, you know, this little one, and then there's this bigger one, right? We have to do them separately and then add the answers together. And I happen to know, just because this one is below the x-axis, this one will be negative. This one will be positive. Right, just because it's above the x-axis. And so our strategy here will be do each integral separately. And then one of them, the one on the left, will be negative. I'll just say make them positive and then add them together. All right, this is our strategy. And what makes this difficult is I never told you where exactly this point is. That's how we're going to split it up. Instead of going minus 10 to 10, I'm going to do it in two parts. One will be minus 10 up to this point, whatever that point is, and then the other part will be this point up to 10. How do you find that point? Again, it is the x-intercept. So this point, again, is an x-intercept, and we can find that using the formula. So the equation is y equals x plus 4. I set the y equal to 0 and solve for x. X equals minus 4. So that's where this point is. It is negative 4. All right. Then my two pieces will be, first of all, the piece on the left will be negative 10 to negative 4, the integral of that, and then the piece on the right will be the integral of negative 4 to 10. So let's do, this is first of all this smaller piece. So to do that, I do the integral from negative 10 to negative 4 of x plus 4 dx. Again, in this problem, you will see the integrals themselves are not hard to do, really. The hard part is just all the setup that you have to do to get to the point where you're doing the integral. So what do we get here? The antiderivative should be 1/2 x squared plus 4x, and I'm plugging in negative 4 and negative 10, right? I plug this in. I get 1/2 times negative 4 squared plus 4 times negative 4. minus 1/2 times negative 10 squared plus 4 times negative 10. All right. This, ordinarily, I would just leave my answer like that. It's some number. But actually, in this problem, I intend to add this onto the other answer, so I'm going to simplify this entirely. This I also expect to be negative, so I'm going to find what that is. You can use a calculator, or this is not so hard to do by hand. And then we're going to have to make it positive and add it to the other one. So let's see, can we compute this whole thing by hand here? It's going to be 1/2 times 16, right? That's negative 4 squared. And then minus 16 here, and then minus, inside the parentheses is 1/2 times 100 minus 40. All right, so this will be 8 minus 16 minus 50 minus 40. That 8 minus 16 is negative 8 minus 10, negative 18. Anybody agree with me or disagree? I think it's negative 18. All right. Yes, I agree. Okay, so that means the left area is 18, right? Remember I said all along, I expect the answer to be negative for the piece on the left, but as an area, the area of that piece on the left is 18. Okay, let's do the piece on the right then. This would be, you know, on the picture. It's the bigger one that goes this way. This is going to be the integral negative 4 to 10. Again, x plus 4 dx is 1/2 x squared plus 4x. Plugging in 10 and minus 4. Let's do it. 1/2 times 10 squared minus 4 times 10 minus 1/2 times negative 4 squared plus 4 times negative 4. All right, and these guys, I'll simplify these two. This is 1/2 times 100 minus 40 minus, this is 1/2 times 16 minus 8. All right, 50 minus 40 minus, this is not 8 there, sorry. This 8, I should have said 16, but you get minus 8 here. My brain was moving too fast for me. 50 minus 40 is 10, minus negative 8 is, I think I did it wrong. Is this one also 18? I was not expecting that. What did I do wrong? 94. I don't know. Maybe that's right. I thought that there was a smaller piece and a bigger piece, but I think I messed up the numbers somewhere. Does anybody feel like I messed up the numbers?
Is it the way the numbers are structured on the integral itself?
No, I don't think so. This negative 4 to 10. I think that's...
Yeah, and then the other one, negative 10 to negative
4. Oh, it's because, okay, it's because right here, this is a plus here, right? It became a minus, but it's plus from here. Isn't it? Should be a plus, a plus, a plus. 50 plus 40, yes, that's going to be much bigger. 98, right? Erase, buddy. 50 plus 40 minus negative 8 is 98. That sounds better to me. All right, sorry for my momentary confusion. All right, what's my final answer? So the area on the right is 98. And so the total area, we add them together. 18 plus 98, whatever that is. It's 116. Is it? I think so. All right, I think that's right. There's a fair amount of opportunity to mess up the numbers, but I think I got it right eventually. What do you think? Any questions about that one? This is a tricky one. You got to set it up right. Split the integral into two parts, and then add the two answers together. All right. These are all the examples that I had to do for you all today. Does anybody want me to talk some more about something in particular? Nobody does. I think what I would like to do then, we still got 13 minutes on the clock. I am going to send you all a link to our class evaluation thing. I'm gonna do this. I'm gonna put this in the chat tomorrow also, but you will. What? Sorry that I didn't get it. I hope that you will be able to do this. You can do it. You got 10 minutes right now. You can do it right now or some other time. I just put the link in the chat. I do appreciate any comments that you have about the class. If there are no more questions, then maybe I would like to suggest that you do the evaluation thing now. Although if you don't want to do it now, then you can do it some other time. And otherwise, I'm going to hang around for my office hours. So if you do have more questions, we can talk about whatever you like. Otherwise, I will see you tomorrow.